Hi everyone, welcome to the first video on integrating powers of trig functions for Math 1452 at Texas Tech University, which is Calculus 2. So in this video series, we're going to be looking at integrating integrals where our integrand is a trig function raised to a power multiplied by some other trig function to a power. So we're going to call these complementary trig functions because they're the ones that typically go together. So for example, that first integrand is sine, a power of sine times a power of cosine. And those typically go together because they're each other's derivatives and integrals. The next example has a power of secant multiplied by a power of tangent. And again, these typically go together because the derivative of secant and tangent can be written in terms of secant and tangent. And lastly, our third integral up there at the top is a power of cosecant times a power of cotangent. And again, these two go together because they're derivatives of each other. So whenever we are solving these integrals, we can actually use the integral techniques we learned in Calculus 1, such as U substitution and rewriting things using trig identities. But there are going to be some tricks to tell which substitutions and identities we're going to use. So overall, our goal is going to be to factor out one of the following expressions. So we are going to have 6. So the first two are factoring out a sine and a cosine. The second two are going to be factoring out a secant tangent or a secant squared. And lastly, we're going to try and factor out cosecant cotangent or a cosecant squared. So thinking about, okay, we can use the strategies from Calculus 1. These 6 expressions have something in common, and it's that they're derivatives of the 6 basic trig functions. So the derivative of cosine, up to a sine, that is. So the derivative of cosine is negative sine, but we can just factor out a sine, and that'll be fine. The derivative of sine is cosine. The derivative of secant is secant tangent. The derivative of tangent is secant squared. The derivative of cosecant is up to a sine, cosecant cotangent, and the derivative of cotangent is cosecant squared. So any of these trig functions that have the co in front, in particular, this cosine, cosecant, cotangent, cosecant squared, those derivatives actually have a negative in front of them, but we can just factor out of the integral and it's not going to impact it. So we are going to try and factor out one of these 6 expressions because we need this expression to cancel out when we do our U substitution. So therefore, once we can factor these out, we can use U substitution in a way where everything will work and we will rewrite our integral completely in terms of U with no x's left over. So let's talk about what our integral looks like, and we know that we have this overarching goal of factoring out one of these 6 expressions, but we can actually take that a little bit further and say, well, if our integral is a power of sine times a power of cosine, then depending on the power of sine and cosine, we can say automatically what we can do every time, and this can become a more algorithmic process where we just follow these steps. So if cosine has an odd power, well, that means that we can factor out 1 power of cosine, so cosine to the first power, and that's going to be, in particular, looking at factoring out that cosine there. And once we factor out that cosine, we may have some left, right? So if cosine has an odd power, that means it's cosine either to the first power or cosine cubed or cosine to the 5th. And when we factor 1 out, then we're going to be left with, for example, if we were having a cosine cubed and we took 1 out, we're left with cosine squared. And so we are going to change that remaining power we're going to change the remaining even power of cosine using the identity. And we're going to use the Pythagorean identity. So we have this Pythagorean identity here, sine squared plus cosine squared equals 1. And we're just going to solve for cosine squared by subtracting that sine squared from both sides. So what we do here is that we factor out one cosine because we know that we're going to need it to cancel out using u substitution. And then any cosines that are left, we're going to change them to sines using this identity. And the reason that we're going to do that is because to solve this integral, we are going to use the u substitution, u equals sine of x. And when we use that substitution u equals sine of x, we know that the du is going to have a cosine term, which we have factored out. So that's kind of the motivation here, is we're going to take out one trig function and convert the rest of the integrand into another trig function that's going to be our u. So that's how we're going to approach things if cosine has an odd power. So if sine has an odd power, it's the exact same process. Everything just flips sine and cosine. So in this case, we are going to factor out a sine of x, and this now has to do with factoring out this one. So again, if we factor out a sine, then we're going to have an even power. So for example, if we had sine to the fifth and we factor one out, then we're going to be left with sine to the fourth. And then we are going to change that remaining even power of sine. Again, using that same trig identity at the front, but now we're going at the top. But now we're going to solve for sine squared by subtracting cosine from both sides. And now that we are going to change our integral in terms of cosine, then we're going to use the u substitution, u equals cosine of x, to solve that integral. So we take out one sine and we change all the rest of the sines to cosine so that we can use the substitution u equals cosine. So this is what we do if one of those powers are odd. And if one of the powers are even, we have to use a trick that's a little bit different. So depending on the strategies that you learned in Calculus 1, you may be familiar with these identities, but you may not be as well, just because they're less common. So if both of the powers are even, so we are going to rewrite the integral. Using the identities where these are sine squared is going to equal 1 minus cosine of 2x over 2. And we have that cosine squared equals 1 plus cosine of 2x over 2. So in the case where both of our trig functions, our power is even, then we're going to have to use these other identities that let us get rid of that even power and change everything to cosine. So whenever we do this, our entire integral is going to change to be in terms of cosine, and we're going to have, it's actually the cosine of 2x now. So we're still going to use our u substitution, that u now equals cosine of x, but it's actually going to be cosine of 2x because that's what's inside our parentheses. So we can use these other identities, again, to change our entire integral to something in terms of cosine, to then use u substitution there. Okay. So this is how we're going to deal with our three cases whenever we have an integral that has powers of sine times powers of cosine. They will always fall into one of these three cases. I might point out that if cosine and sine both have an odd power, you can use one or two, so I or double I, and that's going to be just fine. Either one of those strategies will work. So this is what we do with sine and cosine. So now let's look at secant and tangent. So because secant and tangent, the derivatives are a little bit different. So let me highlight this here. So for sine and cosine, we just needed to factor out one sine or one cosine. For secant and tangent, what we need to factor out for u substitution to work looks a little bit different. We actually have to factor out a secant tangent or a secant squared. So these will work a little bit differently. So let's go through that. So if we have our power of secant being even, remember that we're trying to factor out a secant tangent or a secant squared. So if our power of secant is even, then we can factor out that secant squared. So we can factor out secant squared. And then because we had secant had an even power, that meant we had two secants, so secant squared, secant to the fourth, and so forth. And so we're going to have an even number left. So we are going to change the remaining even powers of secant. And again, we're going to use this Pythagorean identity. So to get from one of these identities to the other, I'm just going to jot a little note here on the side that if we start out with the identity sine squared plus cosine squared equals 1, to get to this identity that involves tangent and secant, we can actually just divide every term in this equality by cosine squared. And then sine over cosine is tangent. Cosine over cosine is 1. And 1 over cosine is secant. So if you know the first Pythagorean identity, you can get the second one just by dividing the entire equation by cosine squared. So we can now use this identity, and we know that secant squared, of x equals tangent squared plus 1. Okay, so we factor out two secants, so that's secant squared to cancel with our u substitution. And then we rewrite our entire integral in terms of tangents. And just to be clear, we're going to use u equals tangent of x, because our du will have a secant squared, and we factored that out just to make sure that we didn't get rid of it so that our substitution would work. Okay. Next, we're going to consider the power of tangent. So if tangent has an odd power, then we are going to look at the other derivative we can factor out. So we are going to factor out secant tangent. And because that took away one tangent, so our power on tangent, if it was odd, was 1, 3, or 5, or so on. And we're going to be left with none, 2 tangents, or 4 tangents, or so on. So we are going to change the remaining even power of tangent using that same identity as before. But this time we're going to solve for tangent by subtracting 1 from both sides. So tangent squared equals secant squared minus 1. And now we have factored out a secant tangent, which was the derivative of secant. So we're going to factor out the derivative of secant and then rewrite our integral using the substitution u equals secant of x. And finally, if tangent has an even power, then what we're going to do is, this one is different than the first two. So we're not going to factor anything out. We're actually just going to straight away use an identity, just like our third case for sine and cosine. So if tangent has an even power, we are going to immediately use the identity tangent squared equals secant squared minus 1. And then what we're going to do is then we are going to use anti-differentiation or integration by parts. So if we have a tangent that's even, we're just immediately going to change that entire integrand to secant. And once that entire integrand is secant, we can either immediately take an antiderivative. So for example, the antiderivative of secant squared is tangent. Or if we have a higher power of secant, we're going to need to use integration by parts. So this type of integral where we just have secants is kind of a special type of integral. So your instructor should show you how specifically to work out that type of integral just because it's a little bit special. So we're not going to do an example of this type of integral in this video series. So I would recommend looking at the other resources that are posted at the same place you found this resource. Specifically where you found this worksheet to see an example of this kind, just because it's a slight bit different and it won't be covered in an example in this video series. So lastly, if we have an integral with the power of tangent, cotangent, and cosecant, well, if we look back out our overall goals, our goal of factoring something out when we have an integral with cotangent and cosecant looks the exact same as whenever we were factoring out when our integrand was in terms of secant and tangent. So this is actually going to follow the exact same rules as the secant and tangent integrals. However, we're just going to use that other Pythagorean identity instead. So just like before, if we know the identity sine squared plus cosine squared equals 1, we can instead divide that entire equality by sine and get that 1 plus, and cosine over sine is cotangent, and 1 over sine is cosecant. So again, if we remember that first identity, we can get the cotangent cosecant Pythagorean identity just by dividing by sine. So this is kind of an overview of what the rules are and how we're going to deal with these types of integrals. So what we're going to cover in the next video is actually working through examples of one type of each of these integrals. So that's all for this video, and good luck.